So in this next video, I wanted to talk about things to be careful about or special considerations for this type of problem. So for things to be careful about, the first thing is that you need to remember to update x. So you're going to start with some x0 that you're given, and then you're going to have x1 is x0 plus h, and x2 is going to be x1 plus h. You're going to go back to the previous one, you're not going to go all the way back to x0, and so on and so forth. And my advice would be to do these first. That way you don't forget, and you know that for each x value you have the correct one written down, and you also know how many steps you're going to have to do. If you just calculate them all at once, it's pretty easy, and you know exactly how many to reach the desired x value where you're stopping. And then after that, oops, I don't need to say after that. After that, you should always keep your x's and y's together. And when I say together, I mean with the same index. So x0 belongs with y0, x1 belongs with y1. Make sure that they're always matching when you're using them. You want to have x0, y0, f of x1, y1, so on and so forth. And the big thing that people get wrong here is that they plug in a value of x too early. So just don't plug in x's too early. And by that I mean, so here when I was doing step 2, I was calculating y2 from y1. So I needed to make sure that when I plugged in an x value, I was using x1 because x1, y1 belong together. There's always going to be a temptation to, you already have x2, you want y2, so we must use that value. And it would have been wrong if I went here and plugged in, 2.2. Because this should all depend on y1 and x1, so I should not have this information that someday x2 reaches 2.2. That's really the biggest mistake I see in this section. And it sounds silly, but even like when I'm doing it, if I'm going too fast, I'll just look back at the most recent x I had, but it's usually one step too far. And then also, don't reuse x0, y0. So always plug in the previous or most recent, whatever's an easier way for you to remember this. To f when you calculate those new y's. And so a generic way you could write this down is that if you have already some x n, y n, like my x1, y1, then when I'm going to my next ones, xn plus 1, yn plus 1, so that's my x2, y2, it's going to be previous x plus step size, so that's like x1 plus h, and that tail's too long. Previous y, so that's like y1, plus h times f evaluated at those previous values. Something that I'll see is reusing that f of x0, y0. You just want to be careful not to do that. that a generic step in the problem. When I gave you the steps, I used 0 because I think that the xn can sometimes be like intimidating for you all. But you could think about it as something that you're kind of iterating. For given the xn, yn you start from, this is how you calculate the next ones. So those are the things to be careful about. And then I also wanted to discuss some considerations of like what the method gives us and how we evaluate that. So what the method gives us. We end up with these yn and xn. And it can be hard to remember like why we wanted those to start. But yn are approximations of our solution to the differential equation y at xn. So that means that y evaluated at xn can be approximated by that y sub n we calculate. So the whole point of this class is that we want to know y of x for an equation, and this is a way that we get kind of close to it. But it's a numerical approximation, so it is subject to error, and we can calculate that error. So error in the approximation is given by, there are two different ways to calculate it. So I will put them both on the same page, I think. But I'm going to stop for a second so you can pause if you need to catch up with writing. And then we're going to put the formulas on the page. So absolute error is going to be calculated as an absolute value, where we think about the difference between the true solution and the approximation. And so that's going to be the absolute difference between y evaluated at x sub n minus y sub n. This does suppose that you can calculate y of x, you know how to solve the differential equation, and just you're plugging in the approximation to see like how good it is. In this section, you'll be given that y of x. You don't have to solve it, but to see how close the approximation is. And then something else that we might care about is called relative error, which is going to be calculated as y of x sub n minus y sub n. So kind of same thing we just looked at there, and it's still an absolute value. Those lines are actually too long. But then we divide it by y of x sub n. And so what relative error is it's going to be your absolute error scaled by, normalized by, or divided by your true solution. And the reason we talk about relative versus absolute error is because like an error of 1 is really good if my if my function is on the order of 100, but it's really bad if my function is on the order of 0.1. So like if you're counting students at Texas Tech, if you're off by 1, that's great. If you're counting like students in your dorm room and you're off by 1, that's less great, is why we would care about relative error. And so in general, but this is like a big caveat, there are exceptions. Smaller step sizes, h, are going to lead to smaller error. And we're going to do one more example in the next video, but I'm going to stop here and then start it after that.